Well, hello, and thank you for joining me for this explanation of the stochastic alpha beta rho nu model. My name is Sarbo, and this model or this presentation is really something that I have created over the last month or so in order to explain and evaluate the S-SABR model and its practical uses within the context of options pricing. So the actual S-SABR model itself is not that difficult to understand, but there's quite a bit of background information that we need to run through. Everything that I'm going to discuss here is essentially based on the original S-SABR paper. It's been almost 20 years since it was released. It's called Managing Smile Risk by Hagen, Lesniewski, Woodward, and I forget the last name, but it's four authors who wrote the paper. And Kumar, that's it. And it's a very, very good paper on a number of different fronts. It is very readable, very easy to understand, but the paper kind of focuses more on the hedging aspects, managing the risks associated with the volatility smile. I wanted to add my own industry-based knowledge and some more technical details with respect to actual calibration and actual pricing to the base of knowledge that this paper will give you. So as you can see, this is an outline of exactly what we will be going through in this video. Now, after introducing the model, I will go into how it is derived at a very, very high level because there's some very complex mathematics involved in it. I want to spend quite a bit of time focusing on the calibration procedure because it's very important to understand how the model is calibrated. And this is a source of considerable confusion if you've never seen it before. Then I want to go over some of the hedging applications of the model, which are very important for anybody interested in working in capital markets and anybody interested in working with a bank on either a rates desk or an equity options desk or an FX desk, even a commodities desk. You need to understand the reasons why the hedges are different under S-SABR than they are under regular Black 76. And then I want to talk a little bit about some of the limitations of this model, because there are certain places where this model is used, but with a number of caveats, because it cannot be used fully for everything that you want to use it for. And I'll go into some of the reasons for that. So why do we talk about implied volatility in the first place? Well, that's because implied volatility is the only parameter in option pricing that is not directly observable in the market. It is, by definition, implied by the pricing model you are using. With respect to options, this is, of course, the Black-Scholes schema from 1973 for most equity options, or the Black 1976 model for options on forwards and futures. Now, everything else you can observe in the market, the risk-free rate of interest, the strike price, the forward price, pretty much everything else, the dividend yield on the stock, you can approximate using a continuous value, etc., etc. Everything else is observable, except for implied volatility. You see a price of the option in the market, your model needs to match that price. The implied volatility is what gets your model to match that market price. It is, again, implied. It is derived from within the model itself. So you'd think that it would be easy to evaluate, but it's really not. The original Black 1976 paper by Fisher-Black himself is a fantastic paper, and I highly recommend you read it if you can. Also, the original Black-Scholes paper from 1973, for which, as you may know, Fisher-Black, Myron-Scholes, and Robert Merton won the Nobel Prize in economics, technically the Bank of Sweden Memorial Prize in economics. It's not an actual Nobel Prize, but the paper itself makes a number of very strong assumptions in order to derive its very famous result. And the strongest assumption that it makes is that implied volatility is invariant across time and across option strike. So if you make that assumption, then you just have a single constant volatility input, which describes the actual evolution of the forward process. Don't be too intimidated by all the mathematics. It's really not that hard to understand. All this says is that the change in the forward rate is a function of some constant volatility and the current value of the forward rate multiplied by a Brownian motion or noise factor, a random walk process, effectively. If you use the methods outlined in the Black 1976 paper using Ito's lemma and the unpacking of the actual Black 76 PDE or the Black-Scholes PDE, then you will arrive at the usual result, the closed form option pricing formula that you see on the right-hand side, where the price of, in this case, a European call option on a forward rate is described with that equation. It's very easy. You can program it into a spreadsheet. Very, very straightforward to price. It's really not challenging at all. All you need is essentially the norms dist function with the flag for cumulative set to true, and then you will be fine. Everything else is very, very easy to price, not a problem. Except there are lots of problems. You see, the 1976 result was devised before we ever observed this idea of volatility smile. Back before the great crash of 1987, volatility smiles didn't really exist in the market. Pretty much the market behaved the way that the formula said it would. But from 1987 onwards, in many asset classes, if not most of them, we did observe a smile in the market. What does that mean? It means that implied volatilities at different strikes are indeed different. And this is a huge problem because under the 1976 formulation, any option that trades at a different implied volatility at a different strike is effectively an option on a completely different instrument. So let's say you're pricing, just keeping it very simple, an option on a futures contract for an equity index, the S&P 500 futures, and you're pricing an option on that futures contract. Well, if you're taking the at-the-money option, that will have an implied volatility of, just making up a number, 30%. But what about the minus 100 point strike, from what the current at-the-money rate is? Well, that will trade at a different volatility. Now, if you assume that the volatility at the money is one level across all strikes, then surely a different implied volatility at a different strike will mean that all other options will be priced using that implied volatility. So you're essentially pricing two completely different options. And this means that when you're trying to hedge the risk of your at-the-money option, you're using completely different hedging scheme than your out-of-the-money option and for your in-the-money option. This means that your hedges are not additive. They are costly and inefficient as a result. And this is a huge problem. This means that this model is not really fit for purpose. Despite its mathematical brilliance, no question, it is too limited in terms of what it can do. Certain products have very pronounced smiles. If you look at the rates market, that's kind of my specialty. I've been working with rates for many years. If you look at smiles observed in the market for swaptions, options on the forward rates for specific swaps. If you look at a 3-month option on the 10-year forward rate, you can see that there is quite a pronounced smile, right? Deep out of the money strikes have a very high implied volatility, much higher than deep in the money strikes. And you'll see a less pronounced smile for some of the other candidates for options, 5-year option on the 10-year rate, the 6-month option on the 1-year rate, and so on and so forth. You just don't see a flat invariant smile. So we need to come up with a solution. Well, various solutions have been proposed. One of them is the local volatility solution proposed by Bruno Dupire, and expanded upon by Derman and Kani in their quite famous sort of interest rate valuation method, as it were. And it's really just a kind of a framework of approaching this problem. Essentially what it says is you calibrate your volatilities across all the strikes. You come up with some sort of function, effectively, describing the evolution of the volatility process. It can be something very simple, such as something that is piecewise constant across strikes, or it can be something more complex, something, let's say, with an exponential component. Whatever you feel best models the implied volatility, for a given range of options across a given range of strikes. You then calibrate that function, whatever it is, however you define it, to return back the exact implied volatilities that you see in the market, which is great. It sounds like a potential solution. The problem is that, as Hagen and others argue in their paper, the local volatility model is not consistent with what you observe in the market. Essentially, their argument is that under a local volatility scheme, such as the one that you just saw, implied vols and forwards will move in opposite directions from what they actually see in the market. And you end up with hedges that are too low in price. So you're actually in danger of substantial mishedging. You're hedging too little against the movement of your underlying rate. And as a result, you're going to be constantly rehedging, and you have no idea why you're bleeding money in your portfolio because of your hedges. So this model as well may not be particularly good. And not only that, but it's not really very analytically tractable either. It's a bit of a challenge to work with. And you'll see that particularly as you get to higher order mathematics with respect to multi-factor models, where local volatility schemes are actually used quite a lot. It's difficult to calibrate to local volatility relative to something like S-SABR or something like Black 76, of course. So Hagen and Lesniewski and Kumar and Woodward propose a different schema where they sort of slightly relax two of the assumptions with respect to the forward rate process and the volatility process in the original Black 76 formulation. First, they say that the forward process, instead of being a straight linear process, is actually what you might call a constant elasticity of variance process. So here you can see the forward rate has an exponent attached to it, a beta process attached to it. And that is a constant. And then the actual volatility is itself volatile. It is itself a stochastic process. And it is described by a second diffusion-based process described here, d alpha t equals nu alpha t dzt, right? So you have these two noise processes, which are linked together by a correlation coefficient. You have this alpha process, which is the so-called volatility. And then you have this nu, which is your volatility of volatility, and that is strictly constant. And then you have this beta process, which determines essentially what the forward rate looks like over time, the distribution of the forward rate process, basically. So these parameters have to be calibrated, and one of them is implied from the calibration process. So you have three critically important constants, as I point out here, and then you have one parameter which comes out of the actual calibration process. It is implied by the model. You don't actually need to you don't need to necessarily specifically compute it yourself. It will come out of the model calibration process. Now, you need to calibrate these parameters yourself, and the code that I've written, which you can download for free, it's all in R, and you can unpack it, you can load up the functions, you can see exactly how it's happening. It will show you how to do all these things. Beta is the parameter that describes the evolution of the forward rate. Nu is the volatility of volatility, and rho is the correlation between the two noise processes I've described before. Now, through some rather tricky mathematics, there's a form of analysis called singular perturbation techniques, which you can use to take this equation here in stochastic form and turn it into something that is more easily understood. Relatively speaking, I realize that is a rather formidable and scary looking equation, and indeed it is. It is quite challenging to look at, but it is the only closed form approximation. It's not an actual closed form, but it's a very good approximation of the actual value and the link between the black or log normal volatility that you observe in the market and the alpha that is used in the actual model. So this equation is central to everything else about S-SABR. It describes how you can get back to market-quoted volatilities from the S-SABR model itself. And this is what will determine everything else in the model calibration process in the way that we use the model, in the way that we do anything with respect to the model. This is the fundamental result. It's the most important equation that you will find in any of these slides. It looks terrifying. It's actually really not. Once you get to grips with it, once you begin to understand it, it's really not that bad. And I'll show you why. So the first step to calibrating this model is to figure out what your beta parameter is. And that's actually the easiest step out of the bunch. There are two ways that you get a closed form solution for this set of equations. One is if beta equals 0, and the other is if beta equals 1. If beta equals 0, then you just have a purely, essentially, like a diffusion-based process where essentially you bounce along on a random walk. And then if you have a beta equal to 1, then you have a log normally distributed forward rate process. So a normally distributed forward rate process and a log normally distributed forward rate process are really the two extremes. Everything else tends to be a mixture in the middle. Now, where is it appropriate to have beta equal to 0? Probably where your forward rates are not likely to go negative. So if you're looking at stock options, for instance, a beta of 0 is probably appropriate. If you're looking at swaptions, on the other hand, where for certain very extreme regimes, potentially the forward rate could go negative if you define the distribution of that forward rate as being normally distributed, then it's a problem and you don't want to set your beta equal to 0. You would rather prefer it to be set to 1. Now, is it really, strictly speaking, all that important? Well, yes, but it's not as important as the other parameters. So in most cases, you can get away with a beta of about 0.5. But there is a way of being a little bit more precise about these things rather than just picking a number. You can actually run linear regression of log forward rates against log implied black 76 or log normal volatilities. And this happens by looking at that big, long, scary equation before and setting F equal to K, where you're looking strictly at the money processes. When you do that, the huge, scary equation actually reduces down very quickly into something where you can take logs on both sides, and then you can clean up a bit, and you end up with effectively a linear process. And this linear process describes exactly how you can run the calibration. All you have to do is take your forward rate data and your corresponding black 76 implied volatility data across a range of dates, preferably monthly, and you'd want to have at least 30 observations if you can get away with it. Maybe you can't, maybe you don't have enough data, whatever, that's fine. But you do a log-log regression, and the result will give you your beta estimate. There is an example in the vignette that comes with the R package, which will show you exactly how to do this. It's very straightforward. Rho, the correlation parameter, actually affects the slope of the model volatility smile, and it's particularly important when pricing risk reversals. Risk reversal gives you exactly the payoffs that you see here. It's a process where you go, or a product where you go long one option and short the other option. And the result is that you tend to make money when risk moves away from a particular point and towards your payoff. So if you're looking at the forward rate to increase, you would potentially want to use a long risk reversal. If you're looking at forward rates to decrease, you'd want to use a short risk reversal. So you can see the payoffs here. You can see that how Rho affects the way that you calibrate to risk reversals in the market. It's very important to get it right for this exact reason. Now, Rho has some odd behaviors, and you'll see this in the Hagen paper as well, where it becomes more strongly negative for certain longer dated option maturities, but this is not a universal rule. So don't take that as given. It's something that you'll see as you test this model through time. New, on the other hand, is the height parameter, and this really determines how well your option prices calibrate or correspond to a very commonly traded product in the market known as a straddle or a strangle. They're really the same product, it's just separated by different strikes. If you have a straddle, it's an at-the-money or really identical strike pair of options where you have a long call and a long put, or in swaps terms, in rates terms, a long pair and a long receiver. And you will make money depending on where the underlying rate moves as a result. With strangles, of course, you are relatively flat in terms of P&L, except at the extremes where you get to a long call and a long put at equidistant strikes from at the money. And that will determine your overall payoff. And of course, if your new is not well calibrated, you will not return back the actual market prices of these straddles and strangles. It's very important to get it right. This leads to alpha. Now, alpha, again, like implied volatility, is not directly observable. Nobody trades on alpha. Everybody trades on black volatility, but nobody quotes alpha in the market. So it's even less observable than black volatility itself, which makes it quite a challenge to calibrate to. But we're very lucky in the sense that the equation that we saw earlier helps us to derive the alpha parameter. And there are a number of different ways to do this. There are lots of different implementations. There's a reference in the references section to a MATLAB article, which will show you how to set it up in MATLAB itself. There is a chapter in a book by Espen Garder Haug from 2007. I recommend you get the second edition because the first edition has a lot of mistakes in terms of the actual formulas. Even the second edition has a few issues here and there, but you will find a partial implementation of the S-SABR calibration schema. I have done the full implementation of S-SABR calibration in R. And again, that package is available for everybody to download. You're more than welcome to look at it. So there are actually really two methods to look at calibration. There are two approaches. The first one calibrates everything simultaneously. You take your beta parameter that you've come up with, that you've estimated separately, and then you take a guess at what your alpha, rho, and nu will be. You feed in your strikes and your implied volatilities at those strikes into the S-SABR calibration routine. It will go away and do essentially what is a non-linear least squares estimation. That's sum of squared errors, really. It will take this big, horrible equation, and it will take your market volatilities, it will subtract the two and square them, it will square the result, and will add across all strikes. And then the calibration routine will keep adjusting alpha, rho, and nu until that sum of square errors is minimized, the absolute lowest level it can be given the constraints that you feed it. And the constraints are pretty strong. Alpha has to be strictly positive, actually. Nu has to be strictly positive. Rho has to be between -1 and 1, because of course it's a correlation coefficient. So these are strong conditions, but generally speaking, you're almost always going to get a calibration unless the market's doing something really, really funky, and that's very, very rare. The second procedure looks at the money only calibration. So you start by feeding it the at the money volatility, and it computes the at the money alpha as a result, and then calibrates the rho and nu that minimize the sum of square errors for all volatilities and all strikes. This is an implied method of doing the same thing. Now, why would you pick one method over the other? Well, it's a very good question. The first method is most appropriate for options where you need to reproduce the most market accurate smile you can, but you're not necessarily fussed about the at the money point. If there's a bit of an error at the at the money point, but everything else more or less calibrates correctly, that's probably good enough. This is appropriate for most asset classes, except for rates. And here's why. In the rates market, the at the money point is by far the most liquid across almost every strike you can name. Everybody trades at the money options. Very few people, relatively speaking, trade deep out of the money or deep in the money options. It's very rare to find that. There are places where you'll find it, but it's quite unusual. So what you definitely want then is a calibration schema that returns back as close to the at the money actual volatility in the market as possible. And that's where method 2 comes in. So if you look at method 1's calibration procedure, it's exactly as I described. You take that huge long objective function that I showed you earlier, and then you find these three parameters such that the sum of square errors is minimized. That's it. The second method requires an intermediate step where you take f equals to k, and then you reduce this big equation down into a cubic. That's really what it is. It's a cubic equation. Now, because it's a cubic equation, if you remember your basic mathematics from high school, a cubic equation must, by definition, always have at least one real root. And because alpha is always positive, In this case, this cubic equation must have at least one positive real root, which means that our job is made substantially easier, because all we have to do is come up with a schema that finds the smallest positive real root of the cubic. This is exactly what is implemented in the R code itself. All you have to do is find this real root, plug it back in to this whole equation. Your alpha hat goes back in here. Everything runs through the same way. You basically do a sum of squared errors for at the money, and you essentially run straight through the same old scheme. They both look difficult and complicated. They're really not. The actual number of lines of code you need to run this calibration procedure is under 20. You can do it very, very quickly. And R has a number of very useful tools and functions that help you to do this. So it's all very well and good that you have these calibration schemas. What does it look like when you actually run them? Well, here are graphs of various swaption rates. And you can see the at the money calibration procedure in sort of salmon pink. You can see the full calibration procedure in green, and you can see the actual market volatilities in blue. And here I presented the calibrated parameter results as well. You can take these results for yourself. The market data are all embedded in the R package. And you can see for yourself exactly how all of this looks. The data are all there. I've got the historical volatility data. I've got the rate data. I've got the forward curves. I've got everything for you there. All you have to do is load it up. The vignette describes exactly how to do it. The help documentation tells you how to do it. It's very straightforward. This is the 3-month 10-year results, 5-year 10-year, as you can see, very good calibrations, generally speaking. 5-year 5-year, and 6-month 1-year. As you can tell, the S-SABR model calibrates really very well to most, not all, but most points in the smile. This is what makes it so powerful. You can run all of this code in just a few seconds, really. It's very fast to run. And if you're interested in true speed and you really know what you're doing, you can implement the same thing in C++, and it will run in basically no time flat. It's really just root solving and optimization and constrained optimization. And as a result, it's really not that difficult to do if you know what you're doing in these coding languages. And you can create some very fast numerical pricers as a result. Now, we get to the point where we deal with the Greeks under S-SABR, and it's not enough just to take the regular options Greeks. So remember, these volatilities that you've calculated are black 76 equivalent volatilities. They're literally black 76 pluggable. So you take the implied volatility that you get from your model, and you can then plug that straight into the black 76 equation to get your option price. This is great. This is exactly what you want. This is exactly what you need. But you need to hedge against the risk as well. And here you have to make some adjustments because you're not dealing with a simple model anymore. You're dealing with a more complex, more rich model, which has a number of interesting features to it. Hagen et al. Go into the details of this in the paper. I'm just going to provide the highlights here. Essentially, there is a backbone, as it were, to the S-SABR model for delta risk, and it implies a volatility component. Now, if you think about it, this actually makes intuitive sense. If you remember how the S-SABR model is defined, you have a stochastic forward rate and you have a stochastic volatility process, and they're linked together by a correlation coefficient. But what does that mean? It means then when forward rates move, volatilities must, by definition, move as well. And this makes perfect sense when you look at the delta component. You see that the delta component under S-SABR is the same as black 76, and then you have this Vega component multiplied by the predicted change in the volatility, the black 76 equivalent volatility, due to a bump in the forward rate. This piece you can implement numerically. It's really not that difficult. Vega is similar. I mean, you also have to make an adjustment there. And again, it comes down to the fact that when you bump vols, technically you're also bumping forwards, right? So in order to calculate this, you can essentially break it down to the Vega under black, which is a closed form solution, very easy to calculate. I mean, it's just literally, a normal density, a Gaussian density function. And then you have to multiply it by this small correction factor. It's a ratio of the volatility under the at the money point in using the S-SABR, actually the given forward rate and the strike, the black equivalent volatility at that point, and then the black equivalent volatility at the money. And once you have that, you've got your S-SABR Vega. Gamma is a bit more tricky because it's a second order derivative. You cannot simply just take this and then differentiate it easily. You have to differentiate everything using sum and product rules and chain rules, and there's quite a bit of mathematics involved, but it's not really that bad. If you cut through all the fluff, you will get to more or less this result. Basically, you will get to this point here, and you will get to a point where you have black gamma, black Vega, and then these numerical terms, which you have to estimate using central difference methods, presumably, is the best way to do it. That's how I've implemented it. And then you get this small deterministic additional factor at the end. These terms can be solved for numerically. And again, the R code does all of this for you. It's all there. The actual bumps are done for you. The actual shifts of the S-SABR volatilities are done for you. The bumps are described for you very easily, and everything is computed for you using a single function. We also have two new Greeks which are introduced for hedging purposes, and they are relevant for P&L attribution as well, though you'll tend to see them more kind of implied in your attributions. They won't be something that you have to necessarily specifically put in there. So you'll see VANA, which is the risk associated with rho, changes to the correlation constant. And when I say correlation constant changing, that sounds contradictory. It's really not. It just means that the correlation value has to be recalibrated from time to time because it's not 100% constant through time. Sometimes, due to changes in market conditions, it will kind of have to be updated. And the same is true of nu itself. That parameter will also have to be adjusted periodically. And really, ideally, I mean, you would want to calibrate them every single day because you'd have to run these calibration routines daily. With respect to beta, you don't want to change that very often because if you change beta, literally everything else changes. And I do mean everything else changes. So if you want to avoid lots of noise in your P&L explains, keep your beta relatively constant. Either stick to 0.5 or recalibrate maybe once a month. Around mid-month is probably best because you don't have to deal with lots of headaches with your month end and closes. Believe me, I know I worked as a product controller for a long time. It's not fun having to explain to financial control, who are looking at it from a balance sheet perspective, all these fiddly mathematical bits which change the income statement. And then you're like, well, it's magic. It's not magic, it's just mathematics, but it's difficult to explain to people from a non-technical perspective why these things have suddenly shifted over time in various buckets. Just do it in the middle of the month when it's a little bit more quiet. You don't have to deal with the headaches of month end. But once you've done it, it's really very straightforward. This again is straightforward to understand. This is straightforward to calculate. These things you can figure out. This is really just Vega, and these are numerical terms that, again, the code does it for you. So can we compare Black 76 and S-SABR Greeks? Well, absolutely. It's quite straightforward to do. So consider, let's say a 3-month option on the 10-year forward rate, which is really one of the most commonly traded products in the swaps market. And I've given you all the parameters on the left-hand side. It's a very straightforward standard option. It's quite a bit in the money, actually. So it's a good approximation of, some of the like products that you see traded right now. 2.5% forward rates or 2.5% strike is potentially what you might see in the market these days. And here are your fully calibrated S-SABR parameters. I've done all the calculations for you. You can replicate these easily enough using code, and you will get the following prices. You will get a Black 76 price. You will get at the money S-SABR price, a full S-SABR price. And then you can see there are pretty decent differences between the Greeks, right? So your delta component has to be adjusted for based on some of the other pieces that you're seeing. It's not enough just to calculate delta and say, in closed form and say, yeah, that's done. No. You would actually be mishedging if you just use this number with this formula. It wouldn't work. Same with Vega. You can see that the Vega has changed very slightly. You can see that Gamma has changed very slightly as well. And now you have these two new Greeks, and Vanna and Volga kind of make sense because, as you can see, Vanna here is SABR rho. It changes to that. Rho is negative in the calibration results, which means that the forward rate and the volatility are negatively correlated. So it kind of makes sense that if you were to bump forwards up, or if you were to bump correlation up, the value of your option would fall. It's to be expected because then the forward rate itself would go down. So you can see that for delta, the Greeks under SABR track pretty closely, except for in this region where you're seeing deep out of the money sort of options. You're seeing a bit of a mismatch there, and again that comes from the backbone correction, and you would expect to see that. With Gamma, again, generally tracks pretty closely, except again in this out of the money region, where you do see a lot more tilt in the smile. You do see that very pronounced tilt in the 3-month, 10-year smile, and this goes a long way to explain the difference in convexity between what you would expect from a straightforward black 76 schema versus a more sophisticated SABR schema. Vega is kind of the same way, and you see now, because of the presence of the smile, you would see quite a deviance, a variation between both deep in the money and deep out of the money. And again, everything is available in the code. Run the vignette, look at it for yourself. It's all there. So now let's look at some applications, because this is a very powerful model for a lot of different things. The most obvious application is for pricing European swaptions. This is the one that I've seen it used for all the time. And you can use it for pricing caps and floors as well, because, those are just a series of options, really, over time. And really, all you have to do, literally, is just take your calibrated SABR volatility, because it's black 76 equivalent. You have your calibrated beta, rho, and nu, therefore you have your calibrated alpha, therefore you have your calibrated SABR volatility, which is equivalent to your black 76 volatility, right? So all you have to do is plug it straight back into the black 76 equation. You get a price, and that is your price, and that is exactly how you would price an option. Now, this won't give you a full term structure of prices, but that's fine. You don't really need one. It's perfectly appropriate for pricing caps and floors, and for swaptions, European swaptions. You really don't need anything more than that. What about Bermudan callable swaps? Now, I did quite a bit of work with these products early on in my career, where I looked at a lot of applications related to pricing callable swaps issued on the back of Fannie Mae, Freddie Mac, and Ginnie Mae type bonds. And the idea behind using these, using the SABR scheme to price these products was that really a Bermudan swaption is essentially the probability weighted value of a portfolio of European swaptions. What do I mean by that? If you look at the valuation of a Bermudan, what is a Bermudan? It allows you to exercise the option to cancel or to call the underlying swap at different time periods, regular intervals, every 3 months, basically. That essentially means that the minimum price of the Bermudan is given by the highest value of the entire portfolio of European swaptions corresponding to that, all of the rates, all of the forward rates implied by that Bermudan. What do I mean by that? If you take a 5-year Bermudan option, callable every 3 months, that means that in order to price this Bermudan, you have to figure out the 5-year rate 3 months from now, the 5-year rate 6 months from now, the 5-year rate 9 months from now, the 5-year rate 12 months from now, and so on and so forth. Every single one of these points can be priced using a European swaption on that forward rate, which means that the maximum, or rather the minimum value of this Bermudan swaption must be the highest value of that portfolio of swaptions, because the value of the Bermudan is a probability weighted sum of the values of all of those European swaptions. The weights are the probability of exercise at any of those given points, and you can compute those through backwards induction. The maximum value of the Bermudan swaption must be the equivalent cap. By definition, has to be the equivalent cap, because that is essentially what gives you the right to exercise an option every 3 months, regardless of whether the trade is in the money or not. You can, each one is an individual option. So that range gives you the ability to approximate the value of the Bermudan. And both the max value European and the cap can be priced using S-SABR, by definition, using the points that I've just raised previously. Another really interesting application of S-SABR comes in the inflation world. Now, I have a lot of experience with inflation derivatives as well. I worked on an inflation desk for a long time. The inflation world is unusual because you have sometimes negative strike options. Why negative strike? Well, essentially what that means is that the trader or the counterparty is forecasting deflation. The rate that is being priced is the forward or future value of the CPI index. And the CPI index is defined by the value of the CPI today divided by the value of the CPI the previous year. The year-on-year change of CPI is essentially what you're looking at. You have year-on-year options and you have one-time options. So basically, if it's a 5-year option, then you look at the CPI rate 5 years from today and you compare it to today, and the change in CPI is your payoff, right? There are times when you will find people pricing negative strike options because they're predicting deflation in the future, or they're just interested in pricing for it. Maybe not these days when you see inflation at, well, officially 9% in the US. Those statistics are garbage. It's really close to 20% at this point. And elsewhere in the developed world, I mean, Estonia, as of the time of this recording, 20+% inflation. Britain, 15% actual inflation. It's really, again, close to 20%. Most of Europe, 12 to 15% inflation. You're not going to see deflation anytime soon, but these products still trade in the market, and you have to figure out how to price those options using a S-SABR technique. Well, you can do that because I know that, having worked with more advanced valuation models, particularly like a 3-factor Jarrow-Yildirim model, which is essentially a Heath-Jarrow-Morton type 3-factor term structure model. That takes a long time to price. With a S-SABR model, you can price the same exact trade very, very quickly. So it's very useful to have this formulation where, essentially, to handle negative strikes, you have this shift option, where the shift option in this case would be, -2%. You just plug that straight in and it shoves everything into positive territory, then you're good to go. There are other versions of this, like there's a Deloitte working paper which has an absolute value of F, which you can also use. But the problem with that is that the results are much harder to program into code. They really are. They're much harder to turn into fast pricing solutions. So people typically stick with something like this instead. In practice, I mean, in practice, you really have to strike a balance between mathematical precision and just being able to do your P&L and risk on time. That's the truth of it. I mean, this is coming from somebody with 10 years of experience in that field. Now, that's not to say that S-SABR is good at everything, because it's not. There are certain things it can't do very well. One of these things it can't do very well, going back to the Bermudan swaptions example from earlier, is pricing step-up Bermudan swaptions. There are certain cancelable swaps in the market where the strike actually steps up over time. So it starts out at, let's say, 2.5%, and then it steps up to 2.8%, and then 3%, and then 3.5%. You're just giving a random example. I'm not saying that's what actually happens, but it's sort of similar to that. What's the appropriate strike? How do you calculate the minimum value and maximum value? It's impossible. at least using SABR techniques, because what is the appropriate strike? You can't take the minimum strike because that will dramatically overvalue the option. You can't take the maximum strike because that will dramatically undervalue the option. You can't take the average strike because, well, how do you know that you've got the right average? You don't. You still have this pricing problem. You can take a kind of linear interpolation of the strike, the so-called Chayette model, I think it is. That doesn't really work that well either. You can't really use SABR for this. You have to use a two-factor sort of quadratic Gaussian mesh type model, or a full, LIBOR market model type approach to something like this. It's not something you can solve easily with a one-factor model. It's just not. You can't use a one-factor HJM model with, or an HJM framework with SABR plugins for the implied volatilities. It won't work. It'll lead to dramatic mispricing. So you can't really use it for those purposes. And again, this is venturing into the realm of fairly advanced derivative mathematics. It's very hard to do. The last example I want to show you where things don't work quite as well as we might like is in the realm of pricing constant maturity swaps. Now, constant maturity swap is an interesting, very challenging vehicle. It doesn't sound challenging because it's just a swap. Well, yes, but it's a swap where the underlying rate, the floating rate, is not LIBOR. It's a swap rate. And the swap rate fixes in a different way than LIBOR does. And it also operates under a different probability measure than LIBOR does. And I don't want to go deep in the mathematics, partly because it's very difficult and I'm not even very good at it, to be honest. And mostly because it's secondary to the purpose. The point is that there is a convexity adjustment. And that's what happens every time you kind of change measure. You'll find convexity adjustments when moving from pricing forwards to pricing futures, for instance, because forwards mature at a particular time, they settle at a particular time, futures settle every single day. So you have to adjust the price using a convexity adjustment to get around to that. Now, with respect to CMS swaps, a CMS product essentially consists of a plain vanilla LIBOR versus fixed swap and a portfolio of swaptions. And those swaptions have to be priced across a very wide range of strikes. So to price the convexity adjustment properly, you have to get quotes from the market at what's the implied volatility for a swaption on at the 10% rate, at the 10% strike on 3-month tenure. 10%? Seriously? Who buys options at 10%? Nobody. So you get these very illiquid points really far out there in deep in the money and deep out of the money, where you have to get quotes. And the problem is that SABR doesn't calibrate that well to really illiquid options because the volatilities bounce around so much at those extremes. So when you have that issue, it's very difficult to use something like SABR to run these pricing schemes. You can run it, but you're going to have to incorporate quite a bit of, shall we say, common sense when you're running these prices, because it's not going to work the way that you expect it to. The prices will be unstable. They'll be very difficult to hedge against. It'll be very difficult to find good quotes in the market, and you'll end up going to 5 different brokers, and they'll all give you wildly different estimates. I mean, one estimate might be 60% at the 10% rate. Another estimate might be 75%. I mean, I'm making numbers up, but you'll get the idea. It's going to be a huge spread. What's the appropriate quote? You just don't know because it's so illiquid. And for that reason, it's very difficult to use SABR at these very, very distant strikes. But it is still possible to price CMS trades. It's not something that's fun to do. So in conclusion, the SABR model is a remarkably effective pricing scheme for what we use it for in capital markets. It does look pretty scary when you look at it the first time. But actually, once you really think about it and you really look at the code, you really try to understand how the mathematics works and you relate it back to the computer code, it's dead easy. It really is. This is not difficult to implement. You have to be careful about the way that you use the Greeks coming out of the SABR model. You do need to keep in mind that there are substantial limitations to some of its applications. But in general, this is really a great model to learn and understand alongside the standard Black 76 and Black-Scholes models. And I highly recommend it to any student in mathematical finance who is interested in this stuff. Take a look at this presentation, take a look at the code, take a look at the worked examples, take a look definitely at the original Managing Smile risk paper and see what you make of it, because this is really a very fun and interesting field. Thank you very much, and please be sure to like, comment, share, and subscribe, and let me know what you think.